Good morning, grade 11. Hope you are all doing fine and being safe. This is Miss Pamela Teeny giving the physics course. Today we are going to continue section 1 in chapter 6, which talks about projectile motion. So please open your books on page 152 and follow up with me. As we already discussed in the previous session, we have two kinds of projectiles. Projectiles that are launched horizontally, like the one you see in the figure to the right in the upper part, and projectiles launched at an angle, like the one you see in the lower part of the figure to the right. In the previous session, we talked in details about projectiles launched horizontally. Today we are going to talk in more details about projectiles launched at an angle. Projectile's velocity. Since the gravitational force pulls downward, gravity will only affect the vertical component of the velocity, Vy, of the projectile. So since gravity only acts in the vertical direction, it will only affect the vertical component of the velocity of the projectile. However, the horizontal component of the velocity, Vx, will remain unaffected and it will stay constant as the projectile moves along its path. So since gravity only acts in the vertical direction, then only the vertical component of the velocity will be affected and it will change as the object moves along its path. But the horizontal component of the velocity will remain constant. As you can see in the figure in front of you, the object is launched at an angle. So at the beginning it has Vx0 and Vy0, which are the initial horizontal velocity and the initial vertical velocity. The vertical velocity decreases as the object is going up. It reaches 0 when the object is at maximum height, and then it increases again as the object is going down due to the acceleration due to gravity. However, the horizontal component of the velocity remains the same along the path. The length of the vector is not changing. This is how we can know that the magnitude of the horizontal velocity is not changing. But the length of the vertical velocity, the vector of the vertical velocity is changing. This is how we can know that the vertical velocity is changing. So it decreases, reaches 0 when the object is at maximum height, and then it increases again. But the horizontal velocity remains constant. Now concerning the calculations for projectiles launched at an angle, first we can find the initial horizontal velocity. So since we have a velocity at an angle, we have initial horizontal velocity and initial vertical velocity. So if we know the initial velocity, we can find the initial horizontal and the initial vertical velocities. To find the initial horizontal velocity, we use the first equation that you see in front of you. Vxi, which is measured in meters per second, is equal to Vi times cosine angle. Vi is the initial velocity that is at an angle, and theta is the angle measured in degrees. And in order to find the initial vertical velocity, we use the second equation you see in front of you. Vyi, which is measured in meters per second, of course, because it is velocity, is equal to Vi times sine angle. Vi is the initial velocity at an angle, and theta is the angle of the velocity. Number 3, to find the horizontal distance traveled by the projectile, we use the first equation you see in front of you. Xf, which is measured in meters because it is distance, is equal to Vx times t. Vx is the horizontal velocity measured in meters per second, and t is time measured in seconds. So it is the same equation for projectiles launched horizontally. Number 4, to find the maximum height above launch level, in order to find the maximum height that the projectile reaches, we use the second equation that you see in front of you. Y max, measured in meters because it is distance or it is height, is equal to negative Vyi squared, which is the initial vertical velocity measured in meter per second, over 2 times Ay, which is the vertical acceleration measured in meter per second squared. Now, in order to find the final horizontal velocity, we use the magnitude of the initial horizontal velocity, since we already stated that the horizontal component of the velocity remains constant, because nothing affects it. Gravity only acts in the vertical direction. So Vxf is equal to Vxi, and they are both measured in the same unit, meters per second, and they both have the same direction, since the direction of the horizontal velocity doesn't change. However, in order to find the final vertical velocity, we can use symmetry, and we will get Vyf is equal to negative Vyi. So Vyf will be a negative number since the object is going downwards, and Vyi is positive since the object is going upwards, and they are both measured in meters per second. And in order to find the vertical velocity at a certain time, you use the equation you see in front of you. Vyf is equal to Vyi, which is the initial vertical velocity, plus Ay, which is the vertical acceleration measured in meter per second squared, times time in seconds. Finally, in order to find the time of travel, we use the equation you see in front of you. T, which is measured in seconds, is equal to VYF, the final vertical velocity measured in meter per second, minus initial vertical velocity measured in meters per second, VYI, over the vertical acceleration, AY, measured in meters per second squared. Now I'm going to state several notes that will help you in solving such problems. 1. Always choose the coordinate system so that the positive x direction is in the direction of the horizontal velocity and the positive y direction is up. So anything horizontal opposite to the horizontal velocity is negative, and anything that is going down or that has downwards direction is negative. Then, if yi is not given, you can use it as 0 meters. You can consider it to be 0 meters. AY and VYF will be negative since their direction is downwards, and AY is equal to negative 9.8 meter per second squared unless it is stated otherwise. Finally, AX, which is the acceleration in the horizontal direction, is 0 meter per second squared. Since the velocity in the horizontal direction remains constant, then there is no acceleration in the horizontal direction. As an example, we will solve example problem 2, page 157. So please open your books and follow up with me. Example problem 2. A ball is launched at 4.5 meter per second at 66 degrees above the horizontal. It starts and lands at the same distance from the ground. What are the maximum height above its launch level and the flight time of the ball? So they need us to find y max and t. The given yi is equal 0 meters since it's not given, vi is 4.5 meter per second, the angle is 66 degrees, and the acceleration in the vertical direction is minus 9.8 meters per second squared. First, we find the y component of vi. So vyi is equal to vi times sine angle, equal 4.5 meter per second times sine 66 degrees, equal to 4.1 meter per second. Then we use symmetry to find the y component of vf. VYF is equal to negative VYI equal to negative 4.1 meter per second since it is in the downward direction. Now we solve y max. Y max is equal to negative VYI squared over 2 times AY. So negative 4.1 meter per second squared over 2 times minus 9.8 meter per second squared equal to 0.86 meters. Finally, we find time. T is equal to VYF minus VYI over AY. So negative 4.1 meter per second minus 4.1 meter per second over negative 9.8 meters per second squared. And the answer is 0.84 seconds. As a homework, please solve numbers 4 and 5, page 157, and numbers 9 and 10, page 158. Your homeworks must be done and submitted to me on Thursday, 23 April. Good luck and stay safe.